Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm going to talk about a somewhat different topic now. This is work that was done with Jacob Erickson, who was an intern with us last summer, and Victor, who hasn't gotten up yet, and Jithu over there. And essentially what we were curious about was whether we could actually have an enterprise, a small enterprise office run completely without wires. Well, you still need the power cords, but you know, by wires I mean the Ethernet wires. And essentially what I mean is, you know, no big mess of wires, no access points. But essentially, if PCs had wireless interfaces on them, really that's, in some sense, that's all you need, right? I mean, you've got your wireless interface, they can do routing, they're powerful enough. You know, if you had a large number of PCs that were doing multi-hop wireless routing, would that be enough to run a small office? And so that, by that I mean there are a bunch of workstations that people are using, and then there might be some servers that you've put in with wireless interfaces that handle mail for these machines. And then, you know, maybe like Active Directory, and then maybe you'd have one or two machines that actually have a physical wire to connect this office to the internet. And I'm not talking about taking an entire large corporation of tens of thousands of machines and converting that all into a single multi-hub wireless network, but rather a small corporation, talking about order of 10 to 100 PCs. This would be useful in the case of where you want to rapidly deploy an office, or it's a short-term office scenario, or it's a low-cost solution. Not looking to actually replace the wire. The wireless technology that's available readily on the market today is not going to offer you the bandwidth that you can get if you were to compare it to like gigabit Ethernet, right? So really what we're curious about is, can you get good enough performance today? And by performance, I don't mean total amount of bandwidth that you can pump through the network, but rather how long would a user wait for a transaction on such a network than on a typical wired corporate network? And by a transaction, I mean if I were to go to CNN.com, my web browser is first going to get the HTML file, so that's one transaction. Then it's going to get like the CNN logo, that's another transaction. How long do each of these transactions take on top of what they already took on the wire, if it was a corporate wired network? So we're looking for small additional delay that the wireless network would impose, a multi-hub wireless network. So essentially, what I mean is every PC has, let's say, two 802.11 interfaces. Why two? Two gives you a lot of nice properties. It lets you simultaneously transmit and receive packets if the two interfaces are in orthogonal channels. And it also gives you nice properties of frequency diversity and rate range trade-offs, which are good if there are other networks that are co-located that might interfere with your network. And also, there are some set of office servers like mail servers, domain controllers, revision control, code repositories that are also part of this wireless network. And a very small number of actual machines that have Ethernet on them to help these users get to the internet. And we assume that there'll be some form of mesh routing going on between all of these machines, which is essentially a multi-hop wireless network where the nodes do not move. There's been a lot of prior work on mesh networking. Most of it in routing protocol design and in link quality metric design, and we feel that it is that this work is mature enough that it's time to ask the question of whether we can run an actual office on top of such a network. So the questions that we want to ask are really, what additional delay penalty will a mesh network impose in a typical office configuration or a set of typical office configurations with typical office traffic? And if an administrator were to design or maintain such a network, they would have a bunch of questions in their mind. What kind of wireless hardware should I pick? Does it really matter? Does it matter whether I'm doing it all on 802.11a or 802.11g? Does the routing metric matter? There are a bunch of different routing metrics that have been proposed in the research literature. Does it matter where I place my mail servers and my domain controllers with respect to all the different users in this network? And also issues of, whether I should really turn on RTS-CTS, should I try to do power control, and so on. So you might ask, well, don't we already know the answer to these questions from the prior work? The typical evaluation that you will see in a mesh routing paper is you randomly pick a sender, you randomly pick a receiver, you do a TCP transfer for a couple of minutes, you look at how much throughput you got, and then once that flow is over, you pick another pair of sender and receivers, you do the same thing again, and you calculate a median based on a certain number of experiments. And then you get some throughput graph where it shows over these 100 flows that this is the throughput that you got. But that doesn't really tell you a whole lot because, for one thing, this is a really, really synthetic traffic workload. I have no idea how this maps onto the traffic load that a typical office would actually impose. And there's no concurrency between these flows, and these are typically in different kinds of configurations that may or may not be realistic when applied to an actual office area. So there are a bunch of questions that we have. And so the methodology that we use to try and answer those questions are basically we wanted to capture traffic from a bunch of office users. In our case, we managed to convince 11 office users to let us sniff all of their traffic simply because they worked in the same group and I could convince them to let me do that. We didn't go with packet level capture because of TCP effects. If we were to capture all the packets that are going on the wire from users who are using the corporate network, we would have a hard time replaying that traffic on a wireless network where loss is so much higher and the throughput is so much lower that you'd run into issues of how do you effectively redo all of the TCP-ness on the wireless network. So what we did was we captured traffic at the socket level. These are all the open calls, the send calls, the receive calls, and the close calls, and a few others. So this was just above TCP. So that makes it really easy for us to replay traffic without having to worry about what TCP would have done. And what we did was we captured this traffic from people on our floor, and we also had mesh machines that were co-located with these users. And we replayed all of this traffic on these mesh machines. And this mesh testbed was using the MCL software that folks at MSR developed, in particular Rich Graves, who is our research area manager, Jitu over there, and Brian Zill, who is in our group, but he's out of the country at the moment. And essentially what MCL gives you is DSR-like routing with a whole bunch of link layer optimizations. There are a bunch of different link metrics that it implements. Like if you wanted to do shortest hop routing, it'll do that. It can even pick routes with the lowest round trip time or highest bandwidth, or use ETX or the WCTT metric. And what we did was we assigned these users from whom we captured traffic to particular mesh machines on our testbed, and we also assigned application servers to some of the other machines on the testbed. There were about 22 machines in our testbed. And the advantage of doing it this way is that it lets us examine several different design choices. What happens if we move the servers around? What happens if we use different wireless networks? And gives us repeatability. And it doesn't actually disrupt the users who are working in the office because we're passively capturing their traffic and then replaying it on a testbed that's co-located with their offices. Now, the capture of traffic was really very different than the typical synthetic workload you'd find in the prior work. There's a lot of different traffic types, a lot of different sizes. There's a lot more concurrency. It's not just one flow going on the network at any point in time. There are many, many flows going on. What we did was we we segregated the traffic by the application. And the way we identified the application is that we looked at what the destination for this traffic was, which was usually servers that we would recognize as email servers or domain controllers, proxies, or Source Depot, which is our code repositories. And once we segregated it by that application, we could then assign servers to different mesh machines and have all that traffic go to and from those particular machines. Now, one thing to note about our methodology is that we captured traffic using a layered service provider, which is an interface that Windows provides for capturing traffic. And while it captures all the WinSock traffic that comes down from the application layer, it doesn't capture certain kinds of kernel-level traffic. And that includes SMB file sharing and NBT. And for our particular set of users, this was in the networking group, none of them were actually using SMB. But there was a significant amount of SMB traffic, about 20%. And we looked at that SMB traffic by doing packet captures at the same time to figure out what that traffic was. And all of it was intrusion detection traffic that our IT people on the second floor were running. They're basically things like scans for files that are known to be bad in the Windows system directories, and so on. So that is a piece of traffic that we missed out on. So this is how we replayed our traffic. We broke the traffic down into sessions. So between an open and a close, that is one session. And within a session, there are multiple transactions. And a transaction is everything that happens from one send to the next send. So you might have, for instance, I'm connecting to a web server. I might send an HTTP command, and then I get many receives for the different kinds of data that I'm getting. And then I might issue another send command that would start another transaction. So we replay all of these. I won't go into the details. We'll replay all of these sessions across the different clients and the servers. And this is the testbed that we replayed it all on. This is about 2/3 of our floor. There are about 22 machines scattered across there. And we were trying out a whole bunch of different configurations that you would want to consider. We tried 3 different kinds of wireless interfaces. At any point in time, we only had 2 enabled to try and figure out which ones worked well. We also tried both A and G and different channels in them. We also tried playing around with the transmit power level. We played around with RTS, CTS. We also played around with different routing metrics, 5 different routing metrics. And we also played around with different placement. We tried a placement where all the servers were in the middle and all the users were at the 2 ends of the network. We tried a placement where the servers were at the 2 ends of the network with all the users in the middle. And a more extreme case where we didn't have any servers. There was just two proxies that were connected to the wired network, and all the servers are behind that. And this is a sample of the results that we found. We examined 3 particular time periods in our traces. A time period when there was a very light load in the network. This was around 9 a.m. And a time period with medium traffic, and a time period with really heavy traffic that was around 3 p.m. on one of the days that we captured. And we replayed all this traffic, and we were looking at the additional time that each transaction took on the multi-hop wireless network than what it took on the wired network that we captured this traffic from, across a bunch of different metrics.
The first time you used the word transaction in the talk. So you captured lots of packets, all right, and you're going to re-put, well, I was actually meant that picture.
Okay.
Oh, I see. This is what we should understand. So what did you do here? You classified flows basically so that you could separate it. Because I would assume a transaction for me would be what? It would be the picture getting displayed on the web page.
That's right. Yeah. A transaction would be, so a session would be, for instance, I open a connection to the CNN.com server, and a transaction would be I issue a GET for an image, and I get the entire image back.
Your focus, which I would accept, is that the wireless impact on sort of bandwidth has to be separated from the delay the user experiences. We're trying to focus on the delay the user would be noticing. Is that the idea that the delay slide that you're starting to show us?
So essentially what I am showing on the graph is the additional amount of time that that it took for that transaction to complete. So that would include both bandwidth issues. So if the wireless network is giving me lower bandwidth, that, and also any additional delay that would occur due to rerouting and so on. Sure, sure. So if anything, this would be more pessimistic.
Right. So let's take the case of the image. Is the delay you show the delay starting to display the image or completing displaying it?
The delay I show is from the start of the send to the end of the last receive.
Okay.
So in the really light loaded case where the servers are in the middle, so you've got the shortest number of hops to get to the servers, the additional delay that each transaction experienced was relatively low. The middle number is the median of all the transactions, and across the horizontal axis it's a bunch of different routing metrics. And it's roughly about an additional 10 milliseconds for most transactions, which is pretty reasonable. The highest, I think that's the 95th percentile, does get pretty large, and those are for really large transactions where it's not an image but a really, really large zip file, for instance. And then in more extreme cases where it's the 3 p.m. really heavy load with the servers as far apart as possible, so it's the largest number of hops to get to the servers, the median delay does go up quite a bit. It now goes up to 30 milliseconds. And a couple of metrics, can even perform really well at all in that scenario. And there are tons of more graphs that we have to examine all those different cases that we considered. So essentially what we found was that in many configurations, the median delay was under 20 milliseconds, which may be good enough for certain kinds of applications. And clearly not for other kinds of applications like file sharing, where you've mounted a file share and you're trying to and you're expecting real-time access. We did find that the 802.11 hardware actually had a significant impact on the performance. Two cards that did 802.11 ABG, right, and were supposed to have the same performance, performed radically different. The band also had a difference, of course, as expected between A and G. And server placement had a huge difference. We didn't get any benefit from playing with transmit power levels or RTS, CTS. And 3 of the metrics did fairly well, and similarly, but a couple of them were really bad. And there are a lot more details in our paper. So what does this mean? We did this study on one test bed with one set of user traces. Clearly, this is not going to map onto, for instance, if you have a bunch of particle physicists who are trying to, transfer large terabytes of data and process that. But for this particular office scenario of about 11 users who are networking researchers and interns, this worked out really well, and we tried a whole bunch of different configurations. And but there's a lot more that could be done to improve performance. Our network does not do any kind of cross-interference detection and adaptation. It doesn't do, for instance, automatic channel assignment. There wasn't any kind of gateway load balancing going on. That was a static assignment. And we also skipped a whole bunch of real-world issues like fairness and security and denial of service issues here. But we think that we're at the point where you could feasibly consider this as a viable alternative in the case of short-term office use or low-cost office use.
Question?
Yeah.
Yeah, just a quick question. Have you guys looked at ultra-wideband, and do you think that that's going to get real? And it might be interesting to look at a study like this for use of UWB interfaces, if you believe that they're actually going to be real.
I think it would be great to redo these studies in with different 802 or even ultra wideband radios and any other kind of radios that come out. We don't have. I personally don't know much about when UWB will happen or if it will happen. I don't have much of an opinion on that. So, but if I had that hardware, I would love to, of course, try it out and see how well it performs.
Have you compared with just flooding the non-routing without flood the packet and see how bad performance would be?
So instead of doing doing single path routing, just flood the packet everywhere.
Yeah.
We didn't try that.
As for me, it seems that people assume it's going to be very bad, but now the research show how bad it could be. So I imagine in a very small place, it doesn't really matter.
Because
we have. I mean, it's easy to see why this is a bad idea, right? I mean, there is severe scalability problems, and the reason we didn't even attempt to do that is because some of our earlier probing used to flood, and even that was in the early version of the protocol, and even that traffic was too much to handle. So forget data traffic, we couldn't even flood our probe problem.
Okay. And also, like in the experiment, it seems like you're assuming a fairly uniform distribution of the nodes. So
right.
assuming there's just one guy in the north and then the rest are all in the south, it seems like
Sure. Right. Yes, it is definitely the case that our node placement was heavily influenced by our office space and where the members of our groups were, and so it is definitely our testbed is tailored to our office environment.
Not just the environment, but also the usage patterns. Like maybe there is just one guy in the north who has the laptop or wants to use the wireless. And the rest are like, depends on who uses wireless in your office.
Sure. In our case, we captured all the traffic coming out of these desktop machines and replayed them on the wireless network.
Yeah, but assuming there's just one desktop in the north, then
okay.
it's kind
Right.
of
Sure.
design.
Sure. Yeah. Oh, absolutely. If the network was far sparser than it is, then yes, we would expect to see really bad performance. And what we were trying to get at is if we had the deployment that we have today in our office, would that be good, right? And it's relatively rare that you're going to have an office where you've got one person who's so far away from all the other offices that you can't form.
Nobody show up yet.
Oh, sure.
Use it.
Right, but except in this particular case, we our scenario, we assumed that these were desktop PCs, which they were, that had wireless interfaces on them, so they would always be on.